I'm Professor Rad, and this is Precalc video 114, inverse functions. In this video, we'll be talking about what it means for a function to have an inverse, and then we'll explore some algebraic as well as graphical techniques for finding the inverse of a one-to-one function. So we're going to start out with a definition and some notation. So our definition says, if f and g are both one-to-one functions, so we need one-to-one functions here, so that if I compose f with g, I get this input back. Okay, so f composed with g is x. And if I compose in the other direction, g composed with f, if I get x out of that as well, then we're going to say that f and g are inverse functions. In other words, they undo each other. So the input of x, f is going to bring the input of x someplace, and then g is going to pick it up and bring it right back to where it was originally. And vice versa. If you give g an input of x, g is going to take that input someplace, and then f is going to take that result and just bring it back to where it was in the beginning. So these two functions undo each other, that makes them inverses. So the notation that we're going to use for inverses is it's going to look like an exponent of -1, but it's not an exponent of -1. Ah! Okay, in fact, we do want to beware that the inverse of a function is not the reciprocal of the function. Those are different things. So we want to be careful. You do not find the inverse just by flipping it. You need to do a little bit of work. So what work are we going to do? How do you find the inverse of a function? Well, I'm glad I asked. Let's find out. All right, so here's how we determine algebraically the inverse of a function. And actually, it's going to guide us graphically as well. So to find the inverse of a function, if I could spell correctly, we're going to switch the x and y values, and we're going to solve for y. So for this example, we're going to find the inverse of f for the one-to-one function f of x equals x over 2x minus 5. So I'm going to start out by rewriting the formula of the function, except I'm going to use the y notation instead of f of x so that we can then apply this process. So I'm going to write y equals x over 2x minus 5. So to find the inverse, I'm going to turn all the y's into x's and all the x's into y's. So we'll get x is equal to y over 2y minus 5. And now we solve. So we're going to solve this for y, and that will be the inverse function. So I'm going to start out by multiplying both sides by this denominator. That's going to get rid of it on the right-hand side. And it's going to make the left-hand side messier, but that's what we should do. So I'm going to multiply both sides by 2y minus 5. So I'm going to get x times the 2y minus 5 is equal to y. And then let's distribute x here. So I'm going to get 2xy minus 5x, and that's going to equal y. So we're not done yet, even though it kind of looks like we are, because we have y equals. So yay, we solved for y. Except this is a situation where if you go to a dictionary and you look up the word redundant, you look it up and it says redundant, see repetitive. So you go to repetitive and you say, all right, what's the definition for repetitive? See redundant. And you just kind of have this feedback loop where you go back and forth between redundant and repetitive and redundant and repetitive. That's what's happening here. We have this feedback loop where y is defined in terms of y. So we're not done solving for y yet. So in this case, we want to bring all the y's to one side and everything else to the other. So I could move this y over here, but then I would have this x on that side. So it's just going to be easier to move this piece, 2xy, over to the other side. So I'm going to subtract 2xy from both sides, and that will give me negative 5x is equal to y minus 2xy. Now, to finish solving this, we want to be able to isolate y. We want to be able to get either y plus a constant, or like y plus x or something, or we want to get something times y, because if we have y times something, we can divide by that something, which is hopefully not 0, and that will give us, then we can divide by that and will give us y by itself. So what we'll do here, because both of these terms have a y in them, let's factor out the y, so that will give us y times something. So if you have difficulty with these kinds of questions, my recommendation is you star this. So this was an example I had to start in my notebook as a Precalc student because I always forgot this trick and it just took me forever to learn it. So once you have all the y's together, you want to then factor out the y, and then you'll be able to divide. So I have negative 5x is y times, remember we're going to get a 1 here, so we get y times 1 will bring us back that y, and then minus 2x. So now that we have y times something on the right, we can divide both sides by that something, and that will give us y. So we end up with negative 5x over 1 minus 2x is equal to y. Then if you want to finish this up, you'll use your inverse notation. So f inverse of x is equal to negative 5x over 1 minus 2x. There we go. That's our inverse function. Now, I do want to talk about how this answer is expressed, because if you are looking for an answer, say on a multiple choice test, or if you're doing a problem out of a textbook and you go to check the answer in the back, you might not get this exact expression. So the reason you might not get this is because they may have written it in a different form, depending on who was writing the solution, or depending on the move they decided to make. Maybe if we moved the 5x over here and the y to the left, then these negatives would be in different places. So you might get a solution that looks like, let me erase and give myself some space here. But you might get an expression where somebody's moved this minus sign from the numerator out to the front. So you might get negative 5x over 1 minus 2x. Or you might have a situation where somebody took this expression and they multiplied the top and bottom by a negative 1. So you would get negative 1 times negative 5x would give you 5x. And then if I distribute a negative 1 to these terms in the denominator, I get negative 1 plus 2x. And if you have somebody who really doesn't like to waste ink too much, they might not like having this minus and a plus, so they could switch these two terms around, and you would get 5x over 2x minus 1. All of these are correct, and all of these are really in simplest form. So they're just variations of the form of this expression. No one is any particularly better than the other. So one thing you want to be careful of is you want to make sure that you are familiar with identifying equivalent forms of expressions, especially a rational expression. You can take a negative that's in the numerator and move it out front. I mean, you could also take a negative that was in the denominator and move it out front as well. Or you can multiply top and bottom, by negative to change the way it looks. Or you could rearrange terms so that your positive term comes first and then you're subtracting the negative term. So that's one thing to be on the lookout for these kinds of questions. Any of these are good answers, but there could be different forms, especially if you're checking answers that have already been written, say in the back of a textbook or in a multiple choice question. So now that we've done an example of finding an inverse algebraically, let's see if I were to give you the graph of a function and we don't know the equation for the function, how could we find the graph of its inverse? For this example, we have been given a graph of a function. It's on a coordinate plane that goes from -4 to 4 in both the x-axis and the y-axis. So this is our function f of x, and over here we're going to sketch its inverse function. So I didn't bother to write out the grid lines this time since it's such a smallish graph, but it goes through the points -3, -2, -2, 0, 0, 1, ballerina point 2, 2, and we have an open circle at 3, 4. So if you want to take a moment and copy down that graph, that's cool. Then you can pause the video to do that, and then unpause, and we'll go through finding or graphing its inverse over on the other side. So to do that, we're going to follow the same basic principle that we had up here at the note from the algebraic technique. Instead, to find the inverse of a function, we're going to switch x and y, and then we had to solve for y, but here we're just going to graph. So we're going to take every point that's a point x, y, and we're just going to switch them, and that will give us the graph of the inverse. So for example, instead of the point 3, 4, the open circle point, instead of 3, 4, we're going to have the point 4, 3. I'm going to go over to 4 and up to 3 to graph my open circle. Then instead of 2, 2, we're going to get 2, 2 because the points are the x and the y are the same. Instead of the point 0, 1, we're going to have 1, 0. Again, we're switching the x and the y. 1, 0. Instead of -2, 0, we're going to have 0, -2. And to finish, instead of -3, -2, we're going to have -2, -3. And then we're going to connect the points. This was a nice curvy function, so we will make sure we have our smooth, our curve over here. So we're going to connect our points like that. And this is f inverse of x. Now, there is another way that you can sketch the inverse of a function, so I'm going to demonstrate over here. Another way to sketch the inverse of a function is to reflect over the line y equals x. So in my heart of hearts, I'm an algebraist. I think better in terms of words and numbers and algebraic expressions. So switching x and y helps me to know where these points should go. But if in your heart of hearts you're a visual person, and this part kind of bugs you, then you can use reflections to sketch the inverse. So to do that, I'm going to lightly sketch the line y equals x. And then if we were to do a reflection over that line, so for example, if I reflect this point here over that diagonal line, it's going to end up over here. 2, 2 is on the line, so it doesn't move. And then the point 3, 4, when I reflect it, is going to go over to 4, 3. Let's see, -2, 0. If I reflect it, it's going to reflect to 0, -2. And -3, -2, when I reflect it, it's going to go to -2, -3. And when we reflect it, right, we expect the shape of this to be reflected as well. So we're going to get the mirror image of the shape. So now we have like a vase over here, if we take those two. And you can see that this reflected function is the same as the one we drew over here. All right, so there we go. That's how you can find the inverse of a function graphically, either by switching the coordinates of the ordered pair and graphing them, or you can visualize it as a reflection over the line y equals x. Either way is going to work. Now, I forgot to do a check on the previous example, and let's do a check here to see if these are actually inverses. So what that means is if I pick an x value if I pick an x value and throw it into f and take that result and throw it into the inverse, I should end up back where I started. So I'm just going to pick a number for us to check. This isn't a proof, but it is a quick kind of check here. So let's say if I start out with x equaling, let's go with -2 here. Let's start with this point. So if I take -2 and I throw it into my function f, the y value here is 0. So it's going to go to 0. Then I'm going to take that value and throw it into what I'm calling its inverse. So when x is 0, I get -2. So we end up where we started at. That's the role of an inverse. That's what inverses want to do. So you could check this in the algebraic example by finding the composition. So you could compose f with g, and it should simplify to be just x. And you can compose g with f, and you'll get the same thing. So the previous example is a little bit algebraically heavy. So what I'm going to do is I'm going to work it out real fast on the board here, and then just kind of show it and give you a chance to copy it down if you want. But if you take my word for it too, then you can just be like, yeah, that looks like some algebra. I take your word for it. Alrighty, so here we go. I found f composed with g, and then could also do g composed with f. It's a similar kind of process. But when I found that composition, I found that it simplified to x. So if you want to pause and copy this down, make sure you're cool with all of that, that's fine. I'm going to just quickly run through it. So our composition says g is the inside function, so we have f of g. So I took this function g, threw it in here, and that meant wherever I saw x in f, I had to put g. So that's why we have this beautiful rational expression up top. And then here we had 2x, so now I have 2 times g of x. Then I I multiplied 2 by this fraction. So remember that when you're multiplying fractions, you just go across the top and across the bottom. So 2 times -5x gave me -10x, and 1 times the denominator kept it the same. Then to simplify this complex fraction, I multiplied the big top and the big bottom by the common denominator, which was 1 minus 2x. So you can see I did that here. And when you do that, 1 minus 2x times 1 minus 2x is going to cancel out. And that'll give you just -5x in the numerator. And then when I distribute the 1 minus 2x to this first term here, it will cancel at the bottom. And that gives me -10x. So that's where this -10x came from. And then I also had to distribute it to the -5. So here's my -5 showing up here, and 1 minus 2x showing up there. Then it was just a matter of distributing that -5 in the denominator. So that's what I did here. And then combining my like terms, these 10x's canceled each other out. And then -5 over -5 is just going to give me x. So as you can see, sometimes if you have a really complicated function, showing that it and its inverse are indeed inverses can be a little bit algebraically complex. Okay, so when we had our technique for finding an inverse function, whether it was graphically or algebraically, our main goal was to switch x and y. So it turns out, when you switch x and y, what that means is the collection of all the x's of your original function is going to turn into the collection of all the y's for its inverse. And the collection of all the y's for the original function is going to turn into the collection of all the x's for the inverse, right? Because if you're switching all the x's and y's, they have opposite roles, whether they're in the function or in the function's inverse. We call the collection of all the x's the domain, and the collection of all the y's the range. So what this means is that the domain of our original function is the same as the range of the inverse, and the range of the original function is the same as the domain of the inverse. So I'm going to summarize that with a note and then walk through an example. All right, so here's that note summarized. The domain of the function f is the same as the range of f inverse, and the range of f is the domain of its inverse. So I have an example here. F of x has a domain of -2 to 7. We're including the -2, but not the 7. And it has a range of -infinity to 3. And we need to find the domain and the range of F inverse. So the domain of F inverse, the domain of the inverse is going to be the same as the range of the original function because we're switching the x's and y's. So what previously had been all the y's is now for the inverse going to be the x's. So the domain of F inverse is going to be -infinity to 3. Similarly, we can find its range. The range of the inverse of the function is going to be the same as the domain of the original. So that's going to be -2 to 7. All right, I'm going to pull up those graphs that we looked at earlier, and we're going to see this happening visually as well. So these are the two functions that we were looking at in a previous example. We have our f of x, and then we had sketched f inverse. So if I look at f of x and I look at its domain, the smallest x value that it has is a -3. And then goes over here up to +3. For its range, it starts here at -2. And then it goes up to 4, but doesn't include it. So these are the domain and the range of our original function f. Now we'll find the same things for the inverse of f. So the domain of f inverse is going to be here at -2. And it stops here at 4, but doesn't include it. Oh gosh, I just realized this should have not included the 3 over here. Well, I don't know if you guys can hear that. It just started downpouring. So I'm going to finish this example kind of quick so I can shut my window. And then we have the range for this one. So it starts out down here at -3. And then we follow it up and it goes to +3. So if we look at these two, notice that the domain of the original and the range of the inverse are the same. And then same thing here. The range of the original is the same as the domain of the inverse. So far we've been looking at one-to-one functions and finding their inverses because our definition for inverse was only for one-to-one functions. But what if I want to undo a function that's not one-to-one? Can we do that? So I'm going to go close the window and then we'll look at an example of doing just that. Alrighty, for this example, we have v of t is equal to 3t squared plus 1. But we've been told that this is on the restricted domain of -infinity to 0, including 0. Let's find the inverse of t. So if I didn't restrict the domain of this function, then we would have an issue. We couldn't find the inverse. And that's because if I think about what this function looks like, it looks like the squaring function that's been stretched a little bit and shifted up by 1, right? So essentially, we're looking at this function here. And this function fails the horizontal line test. So that means it's not invertible. However, we've restricted the domain to be from -infinity to 0. So what that means is we've gotten rid of the right-hand side of the parabola. And we're only looking at that piece. So if we're only looking at half the parabola, now we do satisfy that horizontal line test. So we do have a one-to-one function. So we can find the inverse. So let's do that. In this case, we have t and v instead of x and y. So I'm going to use x and y for the solving component of it. And then at the end, we just have to remember to switch back to t. So instead of y, I'm going to put an x here. And instead of x or t, I'm going to put a y. And to find the inverse, now that we've switched the roles of x and y, we need to solve for y. So I'm going to start by subtracting 1 from both sides. And then we can divide both sides by 3. And then to get y on its own, we want to undo this squaring. So we're going to square root both sides. But remember, when you're solving an equation by square rooting both sides, you have to do the plus or minus. So we're going to get plus or minus this beautiful square root, x minus 1 over 3. Now, I want to simplify this radical. So a radical is considered in simplest form if there's no fraction under the radical and there's no radicals in the denominators. So right now we have a fraction in the radical, so we want to simplify that. So I can rewrite this as the square root of the top over the square root of the bottom. I'm just going to keep that plus minus off on the side here. So we have plus minus the square root of x minus 1 over the square root of 3. And then we want to rationalize the denominator. So we can do that by multiplying top and bottom by root 3. This is because the square root of 3 times the square root of 3 is 3. So we'll have a rational denominator. So multiply top and bottom by root 3. And then if you like, you can distribute that 3 underneath that radical. So we're going to get plus or minus the square root of 3x minus 3 over 3. And the reason we're able to do that is because the 3 is also under a radical, right? So if you multiply 2 radicals, you can multiply their innards together as well. So we get 3x minus 3 all over 3. Now, we're not quite done. We have to change our letters, but also this plus minus is telling us that y is not a function. This would fail the vertical line test, kind of reaching all the way back to the beginning of this video, right? So we have to figure out whether we want the plus or the minus. So this is where we're going to use the fact that the range of a function is the domain of its inverse and vice versa. The domain of the function is the range of the inverse. So because this is what y is equal to, we're interested in the range of the inverse function. So we're going to look at the domain of the original. So our restricted domain was from -∞ to 0. That was the left-hand side of our graph. So that means we're going to want the negatives instead of the positives. If we had restricted our domain to the right-hand side of the graph, so from 0 to positive infinity, then we would have wanted the positive square root. So to finish this up, we're going to write that the inverse of v of t, and we're just going to use t instead of x here. So this is going to be the negative square root of 3t minus 3 over 3. All right, there we go. So this has been our video on finding the inverse of functions. Quadratics made an appearance here just to kind of foreshadow where we're heading next. So in the next several videos, we'll be looking at quadratic functions, and we'll be breaking them down much in the same way that you've likely broken down linear functions before in the past. So we had a nice linear form, y equals mx plus b. Now we're going to have a nice quadratic form where we can pull information just from the form of the function, as opposed to like having to plug in points and find some information that way. So I'm looking forward to seeing you in the next video for quadratics. In the meantime, I hope this was a helpful video for you, and I hope you have a wonderful day. Bye for now.